Hello everyone, this is Shreyas here, your physics master teacher at Vedantu. And today we are going to revise the entire chapter of ray optics, which is very important for JEE, NIT as well as boards. So just before your examination or while you are preparing for this chapter or revising through the problems, make sure you put on your earphones and see this video again and again so you can brush up all the concepts as well as the formula. So let's get started. Now the first important thing that I want to talk about is the kinds of images. A real image is formed when the rays converge at a particular point, like it's shown over here, and it produces a crisp image on the screen. Yes, real images can be obtained on a screen like the one shown over here using some lenses or mirrors. Now the next kind of image that can be formed is a virtual image, and a virtual image is formed when the rays appear to diverge from a particular point like the one shown over here. And the best example for that is observing an object using a magnifying glass. So you are on the other side and the image formed over here is virtual, you cannot touch it. It gives you just the feel as if it's there on the other side. Next, let's talk about reflection. Now the first law says that the incident ray and the reflected ray both make the same angles with the normal drawn to the reflecting surface. Not just that, the incident ray, the normal as well as the reflected ray, all of them are in the same plane. And remember, these laws are not just valid for plane mirrors but also for any kind of curved or spherical mirrors. Now let's discuss the different properties of the images formed by a plane mirror. Like you can see over here, the image size and the object size are always the same. Not just that, the image and the object are equidistant from the mirror. Also remember that the image formed by a plane mirror is virtual. That means you cannot go behind the mirror and find the person behind you. Not just that, it's erect and it is laterally inverted. That means the left of the person is the right of the person inside the mirror. If you take a mirror and place it in the path of light, then the path of light gets deflected by a certain angle. Now that certain angle is called as the angle of deviation, which is the angle which the reflected ray makes with the incident ray. And that angle of deviation for a single surface is given by 180 degrees minus 2 theta. Now if you take a mirror and you rotate it by a certain angle theta, then the reflected ray rotates by twice the angle, which is 2 theta. And if you have two mirrors inclined at a certain angle theta, then the reflected ray's deviation with respect to the incident ray is independent of the angle of incidence, but in fact it depends only on the angle between the two mirrors, and the final deviation is given by 360 degrees minus 2 theta. If you take a mirror at rest and you take an object and move it towards the mirror, you will see that the image velocity is equal to the object velocity but with a negative sign because the directions are opposite, and all of this is with respect to the mirror. But if you keep the object at rest and move the mirror itself with a velocity of v, then you will find that the image will move with twice the velocity as that of the mirror. Now, you might have often visited a barber shop or a salon where you find multiple images of yourself on either side. The reason why this happens is because your image formed by the reflection from the first mirror is going to be the object for the next reflection, and that image will be the object for the next reflection, and that's how you figure out all the images formed by multiple mirrors. Now that we have spoken about plane mirrors, let's talk about curved mirrors. Concave and convex mirrors are nothing but a part of a bigger spherical mirror. When you silver the outer surface, it becomes a concave mirror, and when you silver the inner surface, then it becomes a convex mirror. The center of the bigger sphere which the mirror is a part of is called as the center of curvature, and the radius of that bigger sphere is called as the radius of curvature. The pole is the center of that curved mirror, and the line which passes from the center and the pole is called as the principal axis. When you have parallel rays which are incident on a concave mirror, they merge at a particular point. But in case of a convex mirror, these parallel rays appear to diverge from a particular point. That point is nothing but the focal point and is also known as the principal focus. The distance between the pole and the focal point is called as the focal length of that particular curved mirror, and the relationship with the radius of curvature is given by F is equal to R divided by 2. If you geometrically want to locate the exact position of the image, then you just need to follow some simple rules. Also remember, you just need two rays to locate the exact position of an image formed by a point object. Now the rule number 1 says that when you have a ray which passes through the center of curvature or appears to pass through the center of curvature, it retraces back the same path. The rule number 2 says that when you have a ray which is parallel to the principal axis, then after the reflection, it passes through the focus for a concave mirror, or it appears to pass when extended through the focus for the convex mirror. Now the rule number 3 says when you have a ray which is incident on the pole, then it reflects back symmetrically about the principal axis on the other side. If you want to find out the characteristics of the image formed as well as its location, then you need to use the mirror formula, which is 1 by f is equal to 1 by v plus 1 by u. V is the image distance, u is the object distance, and the values have to be substituted with proper signs, which you have already studied in your 10th grade. Now the image can also be magnified, and the height of the image upon the height of the object is given by negative v by u. Now if this ratio comes out to be positive, then the image is erect. If this ratio comes out to be negative, then the image is inverted. And if the magnitude of this magnification comes out to be more than 1, then the image is magnified. And if the magnitude comes out to be less than 1, then the image is diminished. Also remember, the image can be magnified along the principal axis, and the width of the image upon the width of the object has the same ratio as that of the velocity of the image upon the velocity of the object. This can be used to solve the problems which involve motion of the object or the image. And remember, the ratio is negative v square by u square. The last one is the power formula of the mirror, and the power tells you the degree of convergence or the divergence produced by an optical instrument. If the power is positive, then the optical device is converging, and if it is negative, then it is a diverging device. And the formula for a mirror is negative 1 by f. When light changes the medium, then it also changes its speed and it also bends. This phenomena is called as refraction. Now when the light rays go from a rare medium like air to a denser medium like water, then they bend towards the normal. But if they go from a dense medium like glass to rare medium like air, then they bend away from the normal. Now the relationship between the angle of incidence and the angle of refraction is given by Snell's law mathematically, and it states that sine of incident angle upon sine of refracted angle is constant for a given pair of medium. And if the light goes from first medium to second medium, it's denoted as 1 mu 2, and it's also called as the relative refractive index. Now remember, this is pronounced as the refractive index of 2 with respect to 1. So that can be confusing at times. Also 1 mu 2 is speed of light in the first medium upon speed of light in the second medium. It's also equal to wavelength of light in the first medium upon the wavelength of light in the second medium. This is true because the frequency of light does not change. And also remember, this is equal to absolute refractive index of medium 2 upon absolute refractive index of medium 1. When the light rays go from dense medium to rare medium, there is a chance that the light rays may not come out on the rarer side. In fact, there is an angle of incidence in the denser medium for which the refracted rays make 90 degrees with the normal, or they come out parallel to the surface. That angle of incidence is called as the critical angle, and for all angles of incidences inside the denser medium which are more than the critical angle, the light rays do not emerge on the rarer side. In fact, they get totally internally reflected inside the denser medium. This is the concept behind the transmission of light in optical fibers. Now that we have spoken about plane surface refraction, let's talk about refraction on the curved surfaces. Examples would be like the fossil preserved in an amber glass, or watching through the meniscus of a fluid, or watching those tiny mini objects placed inside a transparent paper weight. Now remember, for every curved surface refraction, Snell's law is obeyed at every point where refraction occurs. Now the mathematical way of locating the image is given by this formula, which is mu 2 by v minus mu 1 by u is equal to mu 2 minus mu 1 by r, where r is the radius of curvature and mu 2 and mu 1 are the refractive indices of the mediums where the refracted ray and the incident ray are present respectively. The magnification of the image is given by image height by object height, which is equal to v mu 1 divided by u mu 2, and this can be remembered easily by remembering a cross over this formula like this: v mu 1 and u mu 2. Refraction also leads us to believe that the pool is actually shallower than what it actually is. So if you are an observer outside the pool, you will find that the apparent depth is slightly lesser than the actual depth. And the apparent depth is the actual depth divided by mu, where mu is the relative refractive index. But if you are an observer inside the denser medium and you look outside, then you will find that the apparent height is taller than the actual height. And the apparent height is given by mu times of the actual height of the object. Now, this phenomena also leads to the apparent shift produced by the glass slab. So if you observe an object via a glass slab of certain thickness h, you will see that the image is formed slightly closer than the actual distance, and that produces the apparent shift. And the formula for the apparent shift produced by the glass slab of thickness h is given by h into 1 minus 1 by mu, where mu is the refractive index of the glass slab. When you have two curved surfaces, it makes up a lens. In case of a convex lens, the rays which are parallel merge at a particular point, but in case of a concave lens, the rays appear to diverge from a particular point when placed in a rarer medium. Now, the focal length is given by the lens maker formula, which is nothing but 1 by f is equal to mu minus 1 into 1 by r1 minus 1 by r2. R1 and R2 are the radii of curvature of those refracting surfaces, and mu is always the relative refractive index. Just like you had rules for locating the nature and the location of the image in case of mirrors, similarly there are very simple rules in case of lenses as well. The first rule says that when you have rays which are parallel to the principal axis, then they meet at a particular point for a convex lens, or they appear to diverge from a particular point in case of a concave lens. Now the second rule says that when you have a ray which passes through the pole, then it goes undeviated on the other side. And the third rule is when you have a ray which passes through the focal point or appears to pass through the focal point, then after the refraction, you will see that they will become parallel to the principal axis. This comes from the reversibility principle of light as well. Also, it's a very good practice to mark and draw all the kinds of images that will be formed by the object placed at different locations, and it's very important that you visualize this, how the image nature changes or the magnification changes for a convex lens as well as for a concave lens. It gives you a realistic feeling of what kind of images are formed by the ray diagram. If you want to find the location and the nature of the image mathematically, that's when you use the lens formula, which is 1 by f is equal to 1 by v minus 1 by u, and v is the image distance, use the object distance with proper sign convention. Notice this formula is very similar to the mirror formula, just that there is no plus sign, instead there is a negative sign. In fact, the formula for magnification along the perpendicular direction of the principal axis is image height by object height, which is v by u. Notice the minus sign is missing over here. And the formula for magnification along the principal axis, that's given by v square by u square. Notice the minus sign which was there in the mirror formula is not there. And it is nothing but the width of the image along the principal axis upon the width of the object along the principal axis. And it is also same as the image velocity upon the object velocity, again useful for solving motion related problems. Similarly, you have the power formula. Notice again the negative sign is missing in case of the lens, and it's 1 by the focal length of the lens. Now, when you have more than one lenses combined together and both the lenses are thin, you can always combine them into one effective lens. And the power of the effective lens is just the simple addition of the power of the individual lenses. Hence, 1 upon the effective focal length is 1 upon f1 plus 1 upon f2, where f1 and f2 are the focal length of the individual lenses. In case of a lens which is silvered on one side, what you need to do is convert it by breaking it up into two lenses and one curved mirror. Now what happens is the refraction happens 2 times and the reflection happens once, hence the 2 lenses and the mirror. Now all of these 3 can be combined together into one single mirror, because the rays which are falling onto the silvered lens effectively return back, so hence it behaves like a curved mirror. Now all you need to do is add the power of the lens and the power of this mirror. That will give you the power of the equivalent mirror. Now we all know the formula for converting power into focal length, and that will help you solve the problem really easily. Now prism is nothing but an object or translucent object where you have 2 inclined surfaces, and the light enters from one of the inclined surface and emerges out from the other inclined surface. If both these surfaces were not inclined, they were parallel, then the incident ray and the emergent ray would also be parallel. But because these surfaces are inclined, you will see the light ray is going to bend. Now there are certain angles which you're supposed to know regarding a prism. So let's talk about it in detail. So starting with over here, the angle which is there between the two inclined surfaces where the light ray bends, that is basically called as the angle of prism. So A stands for the angle of prism, or sometimes it is also referred to as the refracting angle of the prism. Now this angle right over here, which is the incident angle on the first surface, usually called as I1. Then after refraction, this angle is called as R1. Then the emergent angle, the light which is going to come out with the normal, it makes an angle, that is the emergent angle. It's called as I2. And the internal angle over here for this ray is then called as R2. Now these angles are also related to each other. Like you can see, R1 plus R2 is equal to A, which can be proved geometrically. That's very, very important relationship. Also, one more important thing, you can also use Snell's law at both the surfaces. Like if I use it over here, mu will be equal to sine of I1 divided by sine of R1, which is also equal to sine of I2 divided by sine of R2. So obviously you can use Snell's law at any refracting surfaces. Moving ahead to deviation. Like I told you, the light ray which enters deviates. It basically bends after passing through the prism because the angle of the prism is there and it is not that the surfaces are parallel. So this deviation produced depends on multiple factors, including what angle are you making the light incident, what is the material of the prism. All these parameters affect how much does the light deviate by. Now the formula for the deviation is very simple. It is nothing but this incident angle plus the emergent angle minus the angle of prism. Simple. Okay, very, very crucial. Okay, so I1 plus I2 minus A. Again it comes via pure geometry, nothing else. Now like you can see, if I change this angle of incidence, the angle of deviation will also change. But there is a special angle of incidence for which this deviation produced is the least, and that is the case of minimum deviation of a prism, and that happens when both these angles are equal. So when the angle of incidence is equal to the angle of emergence, you will notice that the deviation produced is the least, very minimum deviation. And in that case, the incident angle, like I showed you over here, I1 will be equal to the angle of emergence, which is equal to I2. And the entire situation of the ray diagram is a very symmetric situation. Meaning this angle is equal to that angle, even the internal angles will be equal. So I can say R1 is equal to R2. Alright my dear students, and also you will see that this ray which passes inside the prism is parallel to the base. So this ray is parallel to the base and everything is symmetric. And you can see the deviation which is produced is 2i minus a, which is very obvious because these both angles are equal. So I1 plus I1 will become 2 times I1. So hence the deviation is 2i minus a. I stands for any of these angles of incidence or emergence. If you look at it graphically, the graph looks curved. This is deviation, this is incidence. If you change the angle of incidence, you will see the deviation keeps changing until it hits the minimum value when both incident and emergent angles are equal. And at that particular situation, you will see that the refractive index of the prism is sine of angle of prism plus delta minimum, which is minimum deviation by 2, upon sine of angle of prism divided by 2. Okay, moving ahead. For thin prisms. So thin prism is nothing but a prism where you will see the refracting surfaces are making very small angle with respect to each other. So you can use small angle approximation like sine theta is theta or tan theta is sine theta and stuff like that. When you use these approximations, you will notice that the deviation produced by the prism on that light is angle of prism into refractive index minus 1, and also something worthy to note is that the deviation versus the angle of incidence graph almost is a flat line. Okay, it's not curved so much like for a normal prism. So you will see that the deviation is almost the same for most of the angles of incidence. only for a thin prism. Alright guys, moving ahead now to dispersion. This probably might also remind you of some famous band like Pink Floyd. They have their album art, okay, where you see a prism is there and white light is splitting all the colors. So dispersion is nothing but the splitting of colors into its constituent elements or constituent wavelengths. So this happens because each color, be it red, violet, yellow, whatever, they have different refractive indices. So all colors do not have the same refractive index. So because of which you see their bending, their refraction is also different. So you might often wonder, what is that value of refractive index which is generally given to you? Like refractive index of glass is 1.5. That is the refractive index of the average color. In the case of the visible spectrum, it is the yellow color. So usually they give you the refractive index of yellow color unless specified otherwise. So like you can see over here, the red light deviates the least. So hence the refractive index is also the least. Then you have the yellow color, which is somewhere in between, which has slightly higher deviation. So that is going to have higher deviation. That means the refractive index of yellow color is also slightly higher than that of red. And for violet color, the deviation is the highest. Hence the refractive index is also the highest. Because yellow is the average color, one can also say that the refractive index of yellow color is approximately equal to the refractive index of red plus the refractive index of violet, the entire thing divided by 2. So it's the mean color that is truly the average. So red plus violet divided by 2 gives you the yellow color. You should also know in which order the deviation or the refractive indices are arranged. So red deviates the least, violet deviates the highest. Moving ahead, how much does it spread by is defined by two important parameters. That is, how much is the angular dispersion and what is the angular dispersive power. So angular dispersion is the spread of the light of the extreme wavelengths. So how much does the red and the violet light spread by? So the angle between these two extreme wavelengths is basically the angular spread or just the angular dispersion. If this angle is less, the angular dispersion is also going to be less, and that formula is just nothing but the angular dispersion is nothing but the deviation of the violet minus deviation of red, which is also equal to refractive index of violet minus refractive index of your red into the angle of prism. Simple. What is dispersive power? Dispersive power is how much is the dispersion per unit average deviation. So this light got deviated, this light got spread also. So how much is that spread per average deviation? You can see yellow is the average color. So per deviation of that yellow color, how much is that spread is called as the dispersive power. So after derivation, this is the formula that you get. But if you look at it derivation wise or just the definition wise, it is the angular spread upon the deviation of the yellow color. That's what it is. So when you substitute and derive it, you will get it as refractive index of violet minus refractive index of red upon refractive index of yellow minus 1. That's how it is. Moving ahead, combination of prisms. Very rarely they ask questions on this, but if they ask, the questions are very simple. You can probably get it under a minute. So what you need to understand in these kind of questions is that the condition will be given to you, whether there is no deviation or there is no dispersion, something like that will be mentioned, and based on that you will write down the formula. So what are the two important cases for combination of prism? Number one is the chromatic combination, often called as dispersion without deviation. Always you're going to concentrate on the word without. So whatever is happening without, that is the one you're going to concentrate on. So there is no deviation happening. So when I say no deviation, there is no deviation of the average color. And we all know the average color in our case is basically yellow. So in this case, it is nothing but yellow. So hence, whatever light goes in this prism, it deviates by a certain angle. It is again deviated in the opposite way because this prism is upside down, so it will deviate the other way around. So the net deviation of yellow should be 0. So the deviation of yellow color in the first prism should be equal to the deviation of yellow color in the second prism. That's it. That is the criteria for chromatic combination. The next combination is a chromatic combination where you have deviation but there is no dispersion, meaning the light bends, spreads. Again, in the next prism, which is upside down, it will try to converge because it's obviously upside down, and it converges in such a way that there is no dispersion, meaning that the spreading is not there. The rays of light emerge parallelly. You again get white light. There might be a deviation, meaning if this light was going here, the final light might go here. So there might be some deviation, but there is no spread in the light. So in such a case, because there is no dispersion, like I told you, always concentrate on without, whatever is happening without. There is no dispersion, hence the angular spread in the first prism will be the angular spread in the second prism. This is the criteria for a chromatic combination. That's all you need to remember. Okay, so don't sit and by heart any other complicated formulas. Moving ahead now to eyes and optical instrument. So human eye is a very fascinating instrument in itself, which is naturally given to all of us. So talking about some interesting facts, and then we can go to the optical instruments part. So our eye is nothing but a very flexible lens. It also has a sensor at the back of it, which is also called as the retina. There are also a lot of things which pass on all the optical signals that your eye receives to the brain, where it is further processed to give you the final image that you actually see. This lens is so flexible that you can stretch it, you can compress it, you can strain it, you can relax it, you can change the focal length, you can even open up or close it, so that when there is more light, then probably you do not want so much light to enter your eyes, or when it is dark, you will see that your pupils will dilate to accommodate more and more light so that you can see things clearly around you. So that's how powerful our eyes are. Now, talking about the main physics aspect, we are not going to go into the biology aspects over here. The first thing that you need to know is when you start focusing on objects which are close by, your eyes are under strain. Your ciliary muscles start straining the eye lens, and because of which you find it difficult to focus on objects close by. Now, there is a smallest distance till which your eyes can focus, that is called as the least distance of distinct vision, which is 25 centimeters for an average person. Below 25, things might not be so clear. Although this is an average, keep it in mind that for young people, this distance can be as low as 8 to 10 centimeters. As you grow old, this distance keeps on increasing beyond even 25 centimeters, and that's why you might have to use spectacles. Now, there is also a secondary point which is called as the far point. Like this one was the near point, or the smallest distance till which your eyes can focus under strain. As the object starts going far away, your eyes feel more relaxed. In this condition, sometimes it might happen that your eyes are not able to relax as much as it should, and that's when you have another kind of optical defect. Now, the farthest distance till which your eyes can focus is called as the far point. For a healthy average human being, the far point should be infinity. So you should be easily be able to see distant mountains or even planets and even stars, and your eyes should be in the relaxed condition. Moving ahead, magnifying power. Now, obviously, you might have seen the uses of magnifying glass or even microscope or even optical instruments or things like telescope. What do these things do? They basically magnify. They make you believe or feel that as if the object has got enlarged. They do it by a simple fact, by actually increasing the angle subtended at your eye. The closer the object is, the larger the angle subtended. But if you can't get the object close, no issues. You just increase the angle subtended at your eye. You feel naturally that the object is enlarged. So that's the magnifying power, not to be confused with magnification. Magnification is a completely different thing. Please understand that. This is magnifying power. Magnifying power is nothing but the factor by which the image on the retina is enlarged using an aided instrument. So magnifying power is nothing but the angle subtended by the aided eye upon the angle subtended by the unaided eye. Unaided means without any instrument. If you just look at it, it subtends this angle. But when you see it with an aid like a telescope or a microscope, the angle subtended is much larger. So that's why it's in the numerator, and unaided, which is without the instrument, is in the denominator. So that's the standard definition of magnifying power. Next up are the three basic instruments that you should know in any competitive exams like JEE NEET. So guys, first one is a simple microscope, which is also just called as a magnifying glass. Now when you use a magnifying glass, you ensure that the object is placed between the focus and the optical center so that you get an enlarged image which is virtual and erect. So this is the image, this is the object. You can see it's virtual, it's enlarged, and it's also erect. The magnifying power has two special cases, one for normal adjustment and two for least distance of distinct vision. What does that mean? It means that if you make this image formed at least distance of distinct vision, that means it is as close as possible to the eye. Beyond that, you will not be able to see it clearly. That's the maximum magnification that can be produced, and it is nothing but 1 plus d by f. This d is 25 centimeters for an average human being, just like I told you before. But if you make this image form really far away, then your eyes are relaxed, so that is called as normal adjustment. So understand this, that normal adjustment, the eyes are going to be in relaxed condition. For least distance of distinct vision, they are going to be under tremendous amount of strain. But if you are okay with that strain for a small amount of time, that's fine. You will get a better magnifying power because of this extra 1 over here. Otherwise, it's just d by f, f being the focal length of the lens. Fair enough? Moving ahead now to the compound microscope. Compound microscope is nothing but two simple microscopes you can think of, or two convex lenses one after the other. So this is how it looks like, and I'm pretty sure you would have seen this in either a chemistry or a biology lab class. Now, this kind of instrument has two important lenses, one near the object, that is called as the objective. The one close to the eye through which you are going to see it is called as the eyepiece lens. Now, what happens is, if you look at the ray diagram, it looks somewhat like this. So this is the object, this is the objective lens. The object will form a inverted real image somewhere in between the objective and the eyepiece, and this image is magnified, but you are not going to use a screen to see it because this is real. This is further enlarged using this lens to form the final virtual image. So when you see it from the other side, which is on the eyepiece side, you see a really large image which is virtual but inverted. Keep this in mind. Also, the distance from the objective to the eyepiece lens is called as the length of the microscope. So technically, this is the length of the microscope. Now, the magnifying power for such a microscope is given by these formulas. So first one is nothing but for least distance of distinct vision. That means the image is formed very close to the eye. In such a case, it is the length of the tube or the length of the microscope upon focal length of the objective, which is close to the object, into 1 plus least distance of distinct vision, which is usually 25, upon focal length of the eyepiece. That's for least distance. But if you want to relax your eyes, then the image will be formed really far, and in that case, it is just LD upon F naught FE. So this 1 is not going to be there, that's all. Rest of the formula is as it is. So it's actually simple to remember. L by F naught, L by F naught, D by FE, D by FE. 1 is there for extra magnification. For normal vision, when your eyes are relaxed, then you do not get that much magnification. Last thing is telescope. So telescopes obviously used for seeing distant objects. And again, it also has objective and the eyepiece both. And in these cases, you will see the object is really far, so object distance will be infinity. The image is also formed really far, but the angle subtended is very huge. That's why you feel that the heavenly body or that star or that planet is enlarged. So this is how the ray diagram looks like. You can see the rays are almost parallel because the object is very, very far. Finally, there is an image which is formed somewhere over here, which is real, very small and inverted. And then what you do is, using the secondary lens, again you make a virtual image which is highly enlarged. And again, this happens to be the length of a telescope, the length or the distance from the objective to the eyepiece lens. Now, in the case of telescope, you just have one formula for the image to be formed at infinity. You do not have least distance of distinct vision formula, guys, because you generally do not try to see the Earth or the other planets. You generally do not try to see any other planet at the least distance of distinct vision. You want it to be as far away as possible. That's okay, but the angle subtended should be large. That's it. So in the case of telescope, the magnification formula is minus f0 by fe. Sometimes this minus is not even written. That's okay. The minus sign just signifies the final image is just inverted, nothing else. Otherwise, the magnifying power is just f0 by fe. f0 is the focal length of objective, fe is the focal length of the eyepiece. The length of the tube is f0 plus fe. That's all. Focal length of objective plus focal length of the eyepiece. That's all is the length of the telescope tube. Do not forget to smash that like button out there and share it with your friends who are preparing for JEE, NEET boards and all such competitive examinations, and subscribe to our channel for more such videos. And if you want to know more about me, do not forget you can also follow me on my Instagram handle, that's Shreyas_Vedantu.